In this video, we will be going over how Maxwell's equation falls out of the geometry of the spacetime algebra. Specifically, Maxwell's laws of electromagnetism emerge naturally from the spacetime algebra when considering only the geometry of the algebra. So let's consider a bivector F. Consider a bivector F. The simplest differential equation constructed from this is this right here, just the space-time gradient of this bivector being equal to 0. So that is the simplest differential equation you can construct from it. And this is equivalent, so which is fully equivalent to the forms of Maxwell's equations in a vacuum. In the next video, I will show how that is, but in this video, I'm just talking about how these equations fall out of the geometry. So there are three important parts to understand about this. The first is that no physical postulates were made. So no physical postulates were made. That is, there wasn't, at no point were we like, okay, well, suppose that the field behaves like this, or that the way that space-time, or the way that we do this specific thing gives a specific result that's not inherent to the geometry. We didn't do anything like that. There were no physical postulates made. The second thing is that we considered two things. Considered the geometry of the STA. So we considered the geometry of this algebra. And the third thing is we considered the differential structure of the spacetime manifold. So basically, all we did is look at the geometry of this algebra and then take this algebra and impose it on a manifold, and it turns out that just the geometry, the interaction of the geometry between the differential structure and the geometry of this algebra naturally gives an equation that is the exact same form as Maxwell's equations in a vacuum. So it turns out that this is actually, you can actually construct the same equation without saying that it's equal to 0. So you can reason for Maxwell's equations outside of a vacuum, but so like you can reason for Maxwell's equations outside of a vacuum, but using only geometry as well. So recall from the last video, or actually I won't write this, but recall from the last video that if you have a bivector field, then the gradient of it is a complex vector. So I'll say recall the gradient of a vector field, or the bivector field, is equal to it's a complex vector, so you'll have some vector j plus some vector j2, which has the pseudoscalar times it. So this is a complex vector. So you can say that the gradient of the bivector f is a complex vector here. And just for a rigor's sake, I'll say jk STA1. So the really cool thing about this is that in electromagnetism, it is known that J1 here, this first complex vector, is just equal to the electric current called J, or electric forecurrent J. So I'll say electric forecurrent, and that J2 is equal to 0. And then this was a result of the no magnetic monopoles, that there are no magnetic monopoles. And so it turns out that just the differential structure in general is completely equivalent to Maxwell's equations. So it's not just when you're considering it in a vacuum, but also when you're considering it outside of a vacuum, that the differential structure of the manifold allows for Maxwell's equations. So in the next video, we'll be looking at the relative Maxwell's equations in a vacuum. So we'll actually be breaking this into its relative form.